Hello, Calc AB. Welcome to the beginning of our first chapter on integrals. Okay, so today what we're going to do is talk about something called a definite integral. And a definite integral is a pretty exciting, important thing. And what it represents is the area under a curve from A to B. So that's our definition of a definite integral. So what I mean by area under the curve is if you have some graph of a function f of x that looks like that, and you have, some a and some b, if you wanted to find the area under that curve but still above the x-axis, that pink area right there is what we're trying to find. And this is one of the first real questions that calculus invented to solve in a simple level is if you have some function, what is the area under that function from a to b? And we write it using this little crowbar little notation. It's a big S. And basically you have a to b of your function, and then you write a little dx. And we'll talk about that in a minute. But the f of x, that is the function you are taking the integral of. So that's the function. And then the a is like your left bound, and the b is your right bound. So whenever you see something like this integral, and it's pronounced integral a to b of f of x, that just means the area under f of x from a to b. That's what it represents. So I should have left more room for this, but the dx, by the way, that's just part of the notation. It's a part of any integral notation. Basically what it means, and we'll talk about this more later, is just a very small change in x. But for now, any kind of integral sign or any kind of integral you write should always have a dx kind of at the end. Okay, so here's a graph of function, here's f of x, and in this example I asked you to find the integral 0 to 6 of f of x. So that just means the area under the graph of f from x equals 0 to x equals 6. That's what they're asking you to find. Okay, now I'm going to start with just some easy cases today. What if we just have this? All right, so, we could break this into two parts, right? We have a rectangle and we have a triangle there. So if I draw a vertical line, okay, so the part on the left, it's a rectangle. So it has a base of 2 and a height of 4. So the area is 2 times 4. So I'm just going to take the area of a couple different shapes and add them together. If I want the area of the triangle, that area has a base of 4 and a height of 4. So it has an area of 8 as well. Okay, so if I want to find that integral is just adding those areas together, which is 16. So that's what you're doing on a problem like this. You're just finding the area from 0 to 6 between that curve and the x-axis like that. Okay, so let's get to the next problem here. What if I asked you to find, given this graph of f, what if I asked you to find the integral from -2 to 3? So let's see, here's -2, and then here's 3. So I see two different bits I'm going to have. I have this triangle over here on the right side. That's going to be pretty easy, right? We see that triangle has a base of 1 and a height of 3. So that's going to be a 3/2 for that little pink area in there. What about this semicircle in here? What is the area of that semicircle? Well, we know the area of a circle is pi r squared. So this is half of a pi r squared. Okay, well, what's the radius? Well, if we see the center is the origin, we see we go 2 units right or up. So the area of that is 1/2 pi times 2 squared, or just 2 pi. So if I were to add those together, that area there is just 2 pi plus 3/2. Now, one new kink here that we want to talk about, if you have area below the x-axis, like this area here from -7 to -2, what we're going to do is we're going to count that area as a negative because we have a negative function height. Like that, the height of that f of x is negative. Okay, so if we have this area in here, well, let's see what this area is. It's a triangle, it goes 1, 2, 3, 4, 5. Okay, it has a base of 5 and a height of 1. So that's a 5/2 for that area, that red shaded area. So if I'm trying to go all the way from -7 over to 2, well, I'm going to have a -5/2 because that's under the x-axis, plus the 2 pi above, plus the 3/2 above, adding those together. Okay, so anyway, that's like 2 pi minus 1. That's fine. But the important part here is that any area that's above the x-axis with a positive height, we count the area as positive. And we're just doing today squares and triangles and semicircles and kind of easy things like that. And anything below is going to be a negative value. So that negative right there is the key. Okay, now one other thing I wanted to point out. If you can draw a graph of the function, it's pretty easy to calculate these integrals. So when you see integral 1 to 5 of 3 dx, that's like saying you have the graph of y equals 3. You guys know what that graph looks like, right? It's a horizontal line at y equals 3. It looks like that. So if you have this horizontal line at y equals 3, and you're starting at 1, and go 2, 3, 4, 5, up to 5, it's just asking you to find that area in there. Okay, well, when you look at that area in there has a base of 4 and a height of 3. So that area is 4 times 3, which is equal to 12. And same thing if you have something like this, like integral 0 to 2 of x. So what that looks like is y equals x. So we graph the function y equals x. And it's just saying find the area from 0, oh geez, that's a bad line. Find the area from 0 to 2, so that's x equals 0, that's x equals 2. Find the area under the curve right in there. Okay, well at 2, this is the point 2 comma 2, of course. And this just means, this is just integral 0 to 2 of x dx, that area, and we're always thinking about these in area. That area just turns out to be 1/2 times 2 times 2, so just 2. Okay, one other one. How about this one? Integral 2 to 2 of ln of cosine of x squared. So if you graph this, well, I don't know what this graph looks like. You probably don't either. So what this is saying, though, look at this. So this is saying the area from x equals 2 to x equals 2. So if I start at 2 and end at 2, does that area have any width? No, right? That area has no width. And if that area has no width, that implies there is 0 area right there. Okay, so that area is 0, and that's always going to happen. That will always be the case, always 0, if the bounds are identical. So if you start at 2 and end at 2, you start at 10 and end at 10, you have 0 area in there. And remember, everything in these definite integrals is coming back to area under the curve. It's because when you see this integral 0 to 2 of x, it just means that the area under x, under y equals x, from x equals 0 to x equals 2. That's how you're doing, and you want to be thinking about these problems. Okay, let's go on and talk about just a couple properties about these that I think we'll find helpful. All right, switching the bounds. If you have the integral 1 to 8 of f is 6, then the integral 8 to 1 of f is negative 6. Basically, you're going backwards. So what this is saying is that if you switch the bounds, all it does is it switches the sign of the area. Just like going upside down switches the sign, going backwards switches the sign. Okay, next one, splitting it up. Do you think the area from 1 to 8 is equal to the area from 1 to 4 plus the area from 4 to 8? Yes. Like, hopefully that makes sense, right? That's what we were doing up here. When I had to find the area from 0 to 6, I found the area from 0 to 2, and the area from 2 to 6, and then added those together on this problem. So hopefully that makes sense. Okay, let's do some example problems just so we can see some problems using these. So the integral 0 to 10 of f is 7, integral 0 to 8 is 10, find the integral 8 to 10. Now the bigger one is 0 to 10, so let's split this up. So what we're saying is if we integrate 0 to 10 of f, that's equal to the integral 0 to 8 of f plus the integral 8 to 10 of f. And we're going to treat that whole integral just kind of like a constant. Or not a constant, like a variable. So when we say integral 0 to 10 of f, that's 7. So that's saying 7 equals 10 plus integral 8 to 10 of f of x. So then going backwards on that, that's saying that, okay, integral 8 to 10 of f, you can subtract that, is equal to negative 3. You can get a little more complicated on one of these. Say you have integral 0 to 10 is this, and then that. So, okay, but look, that's 5 to 0. Okay, so if we know that integral 0 to 10 of f is equal to integral 0 to 5 of f plus integral 5 to 10 of f, which is what we're trying to find. Now, if I know that integral 5 to 0 of f is negative 6, can I use that to find the area from 0 to 5? I think I can, right? It just switches the sign. So that's the logic we saw up here. So that means that the integral 0 to 5 of f would not be negative 6, but it would be positive 6. So that would say 17 equals... Okay, and then that's positive 6 plus integral 5 to 10 of f. So that tells you that, sorry, I kind of ran out of space, the integral from 5 to 10 of f of x dx is equal to 11. So basically, the key here is to split it up. And then on this one, I'm kind of switching the bounds around, which switches the signs. That's a property there. Okay. One other thing like this here, if you have two that are added together, just like a derivative and just like a limit, you can split them up. So you can split this up into, say, okay, instead of finding the area of f plus g, let's just find the area of f plus the area of g. And in this case, that would just equal, let's see, area under f is 3, area under g is 5, so that gives you 8. So we can split this up across addition, just like everything else we've worked with this year. One more thing with constants, right? If you have 3 times a function, you can pull the constant in front, also just like derivatives and limits, which is kind of strange here. So this is just 3 times integral 1 to 4 of f of x, which of course is just 3 times, they told me that's negative 2. So we're just talking about properties, but this makes sense, right? Because if the function under something is negative 2, if then you make that area 3 times as big, that function 3 times as tall, the area is multiplied by 3. Okay. So here's another example here. If integral 0 to 1 of g is 3, integral 1 to 0 of h is 5, right away you might want to swap this and say, okay, that's backwards. That means integral 0 to 1 of h would equal negative 5. Then when you have something like this, 5g of x minus 2h of x, split it up. Turn this into 5 times integral 0 to 1 of g minus 2 times integral 0 to 1 of h, and then you can plug in the values that are given. So we know that this is 3, so that's 5 times 3 minus 2 times, okay, and then integral 0 to 1. We knew 1 to 0 is 5, so that's negative 5, so that's 2 times negative 5, so I got 15 plus 10, which is 25. So that's how we do a problem like that. Just like with derivatives, we split it up into different parts. Okay, and one more thing I wanted to mention just briefly, the variable does not affect the value of the integral. The answer to that is no. So if I find the area under a curve, say from 1 to 3, that's the exact same as finding the area under the curve from 1 to 3 of f of, I don't know, like t dt. Because I'm just finding an area. It doesn't matter what variable I use. It's just the same area, and that's how you want to think about that. Okay, so that's our introduction to definite integrals. I hope that was helpful. We're thinking about all these as area under curves, and then going over some of these cool properties on the back. And bring me questions to class. I'd love to help you out. Thanks.